In this lecture, let us discuss on demodulation of single sideband modulated signal, amplitude modulated signal. So we have already talked about demodulation of SSB waveform to some extent, but I like to come back to the demodulator in detail now. This is more or less like the demodulation of your DSB signal. The same demodulator you can employ to demodulate your single sideband modulated signal. Okay. So we can use a synchronous modulator. Synchronous demodulator, or you can also call coherent demodulator. This we already discussed to some extent in one of the previous class. And again, the synchronous demodulator requires to have a local carrier. So without local carrier, you cannot realize the synchronous demodulator. Okay, and this local carrier has to have frequency synchronization and phase synchronization. So now then the second one is carrier reinsertion, that we will discuss a little later. So mainly we are going to discuss two methods to demodulate the SSB signal. Okay, the second one is carrier reinsertion method. Now let us first talk about synchronous demodulator. Or coherent demodulator. Okay, this we already discussed when we were discussing the demodulation of DSB signal. Okay, so remember we carried out this for the DSB signal. We understood that due to the phase offset, the signal will be attenuated. Due to frequency offset, there is something called a warbling effect. So these are the two things that we already discussed. Okay, now now let us continue this for our single sideband modulation also. Okay, single sideband modulation, how we can demodulate. Okay, so what will be the case in the SSB? Suppose you are using a coherent demodulator, and if there is a phase incoherence, what will be the effect? So we want to discuss effect of phase incoherence. The demodulator is same, x SSB of t, and you multiply by cos omega ct, and then put a low pass filter, and then you will get a replica of the message signal m of t. Okay, therefore now let us discuss effect of phase incoherence. To do that, we have a mathematical representation of the SSB signal. What is the SSB signal? If you recall, we discussed in the last lecture 1 by 2 m cap of t. Actually, AC times 1 by 2, let us assume AC is equal to 1. Okay, to make it simplicity, or you can keep it no issues. After all, it is a constant, right? AC times m cap of t cos of 2 pi fct, then plus AC by 2 m cap of t sine of 2 pi fct. This plus sign indicates we are retaining the lower sideband. Plus means, minus means we are retaining the upper sideband. So either of these two is fine in a coherent demodulator. You can use upper sideband or lower sideband, doesn't matter. Now this received signal is multiplied by this guy cos omega ct. Okay, so AC by 2 m cap of t cos of 2 pi fct plus AC by 2. This is not m cap, right? I am sorry, this is m only. Only the quadrature part becomes m cap of t sine of 2 pi fct. The whole thing is multiplied by cos omega ct. I put some multiplier 4 here. Okay, so you take this SSB signal, this is your SSB signal, and multiply it with the cos omega ct. That is what the coherent demodulator does, and pass it to a low pass filter. The low pass filter is here. It is a very simple trigonometric exercise. Okay, for convenience, let's multiply with the 4 here, 4 times cos omega ct. Okay, if you do the multiplication term by term, then your demodulator output, let me straight away write down the result. Demodulator output, let me denote by y suffix d of t is equal to, in the carrier let me consider time varying phase. Okay, therefore let me put theta of t here, time varying phase. There is a phase offset which actually can model both the phase offset as well as frequency offset. For example, the frequency offset is a time varying phase offset. That's why I put a theta of t. Instead of putting theta, I put a theta of t. So therefore it captures frequency offset and phase offset. So the more general expression is cos of omega ct plus theta of t. Okay, once you multiply this signal with the cos omega ct plus theta of t and then pass it to a low pass filter, your demodulator output will be y of t is equal to, it's very simple. Okay, if you do that, maybe I'll write down here. If you multiply AC by 2 m of t cos omega ct times cos omega ct plus theta of t, right, plus AC by 2 m cap of t sin omega ct times cos omega ct plus theta of t, and there is a 4, and if you multiply by 4 then this becomes 2 times AC, and this also becomes 2 times AC. Now cos A, cos B, that is cos of A plus B plus cos of A minus B. Therefore 2 times AC m of t multiplied by cos of A plus B 2 omega ct plus theta of t plus plus cos of A minus B, that is theta of t. This is the first term, divided by 2. This 2 and that 2 will get cancelled, plus 2 AC m cap of t sin A cos B. Again you can use the trigonometric identities. Okay, sin A plus B plus sin A minus B. So sin of A plus B is like 2 omega ct plus theta of t sin of A minus B is equal to theta of t. Okay. Now whole divided by 2, and this 2 and that 2 will get cancelled. If you pass it through a low pass filter, the low pass filter will remove this component because the frequency is 2 times, and this guy also removed. and it passes this component and this component. Therefore, your output of your low pass filter Yd of t is equal to AC times m of t cos of theta t plus AC times m cap of t sin of theta t. That's it. So that's what you got the output here. Okay, therefore Yd of t is equal to let me take AC equal to 1. Therefore m of t times cos of theta t plus m cap of t sin theta of t. Okay, therefore both the frequency offset and the phase offset will be captured by this theta of t. Okay, after low pass filtering you will get this expression. This is after low pass filtering. Now let us consider the case when theta of t is equal to 0. There is no phase offset, no frequency offset and no phase offset. What is the meaning of this one? No phase offset and no frequency offset. So in this case what will happen? Your Yd of t, your demodulated output will be same as m of t. M of t times cos of 0 plus m cap of t times sin of 0. Therefore, your demodulated output y dt of y of t is equal to m of t. So, whatever you transmitted, the same thing you are getting in the output of the low pass filter. So, this is possible only if you have a perfect synchronism and a perfect coherence output. Okay, perfect coherence. Therefore, output would be equal to m of t. Okay, so theta of t is equal to 0 for perfect replica of m of t. So this is one condition. Now next let us consider if theta of t is not equal to 0. Okay, when theta of t is not equal to 0, then you have a problem. You have a highly distorted signal, right? In if you recall, in DSB SC, we had your y of t is equal to m of t times cos of theta of t. If theta of t is equal to 0, no problem. If theta of t is equal to pi by 2, then what will happen? This m of t will be 0. Okay, but in SSB, in addition to this m of t cos theta of t, you have one more term, m cap of t sin theta of t. No, sorry, not this one. You have one more. You have one more term. Okay, so still it is very complex in SSB than your DSB. Therefore, your theta of t is not equals to 0, then in SSB y of t is equal to m of t times cos of theta of t plus m cap of t sin of theta of t. So this will lead to, if theta of t not equals to 0, this will lead to a highly distorted signal. Okay, so something else is added to this. So this is your m of t times cos theta of t, and something you are adding again to this guy. Okay, so theta of t is not equal to 0 implies a highly distorted signal. So this shows that if I use a coherent demodulator for demodulating SSB signals, it will be even more sensitive to frequency and phase offset than the DSB-SC signal. After all, in DSB-SC, you have only m of t times cos omega ct, but here you have one more term, addition term. So this guy will add to the first guy, second term will add to the first term, and even more worse now in the coherent demodulator. if the phase and frequency are not synchronized. So that is something we have to keep in mind. Okay, now fortunately it is possible to demodulate the SSB signal with the better tolerance to phase and frequency offset, which can be done by something called manual tuning. Manually tuning the receiver, okay, by another method which is called the carrier reinsertion method. So now let us discuss the second method, carrier reinsertion method. So this is a second method of demodulation of SSB signals. And this also requires a local carrier like your coherent demodulator, the standard coherent demodulator, but this has some minor advantages over the coherent demodulator in terms of practical implementation. Let us see what are the advantages that we can get using this method. Basically here what we do is take the incoming modulated signal X SSB of t, and instead of multiplying you add the carrier. Okay, in the previous case we put a multiplier, but here we put an adder. So the carrier is added here, cos omega ct. You put some constant k, it can be anything, simply I am using k here, some constant. You can use a suffix c times cos omega ct, doesn't matter. Now the output contains summation of the input signal and the carrier component. Okay, so instead of multiplying with the local carriers, we simply add. We are doing the addition with the local carrier. So when you add the local carrier to the incoming signal X SSB of t, what do you think you will get now? In this point you will get X SSB of t plus k times cos omega ct. Okay, so we will get a signal whose, if you add these two guys, we will get a signal whose envelope approximately under certain conditions follows the envelope of the message signal. So more or like we are making it in terms of like amplitude modulation with the carrier. Okay, now if you look at as it is now, it is not obvious at all. So now we will see how it becomes. So what we can do is, following this up, you put an envelope detector. Instead of low pass filter, you put a envelope detector like your diode, and put a capacitor and then resistor, that's it. Okay, so let us consider this envelope of the signal at the output of the adder. So this is the output of the adder. Let us consider my E of t, envelope of the signal. Before that, what is my E of t? E of t is equal to X of t, incoming signal, plus your local carrier k times cos of omega ct. Now add these two guys. What is X of t? This is AC by 2 m of t cos omega ct. We are retaining the lower sideband, so I will put plus here. AC by 2 m cap of t, Hilbert transform of m of t, sin 2 pi fct, the whole add with the carrier component Ka times cos of omega ct. Now rearrange this expression. AC by 2 m of t plus k multiplied by cos omega ct plus AC by 2 m cap of t sin of 2 pi of ct. This is the output of the adder. What is this? Output of the adder. Now this is given to the envelope detector, and this is the in phase component y cos omega ct. There is no phase change, but here it is sine. Sine means 90-degree phase shift. Therefore, this is called a quadrature component or quadrature part of SSB signal. So, one of the very nice advantage of quadrature representation of this kind is various kinds of amplitude modulated signals like DSBSE, DSBAM, each of them fall into this representation. For example, in DSBSE we said m of t times cos omega ct. So, it is a DSBSE signal in terms of in phase component. Whereas the SSB signal, it has the extra term. What is that extra term? This extra term. So, the quadrature phase part is the Hilbert transform of m of t. Therefore, this is in conformity with our discussion on the general representation of band pass signals. Recall from the general representation of band pass signals. Therefore, whatever we are deriving here, it is in conformity with our discussion on the general representation of band pass signals. Again, the band pass signals has an in phase part and a quadrature phase part. Please recall. So, any band pass signal can be represented in terms of in phase part and quadrature phase part. Only thing is there is a special relationship between the in phase and the quadrature phase parts for it to become an SSB signal. Now, one of the advantage of this representation is that you can easily identify what the envelope of the signal will be. Okay, so this is my E of t. From this I can find out envelope. Okay, if you remember, what is the definition of envelope? It is the trace of the positive peaks of the carrier. Trace of the positive peaks of the carrier. Okay, so to understand how we can identify the envelope, one can rewrite this equation as follows in the form of amplitude and phase form. So, that E of t can be written as in order to find out the envelope, we can write as R of t times cos of omega ct plus theta of t. Using some simple trigonometric techniques, you can find out this. Okay, to identify the envelope, let me call this is equation number 1 and this is equation number 2. From 1 we can write 2. Why? To identify the envelope very easily. Okay, so equation 1 can always be written in the equation 2 form using trigonometric identities. Now, what is this R of t? R of t is a amplitude part. Okay, and this amplitude part is always positive because it's a magnitude, right? It is always positive. Now, one can ask in general what will be R of t? It will be the square root of, suppose you have a number x plus jy. What is the magnitude of this? R is equal to square root of x squared plus y squared. Similarly, here the magnitude is square root of square of this component plus square of this component. Okay, so square root of 1 by 2 AC m of t plus square of AC times m cap of t whole squared. That's it. Okay, this is the envelope now, or amplitude part. What about the theta? Theta is equal to tan inverse of imaginary part divided by real part. Here imaginary means quadrature part. So this is the imaginary part. Instead of imaginary, I have quadrature part. So this is 1 by 2 AC m cap of t whole divided by 1 by 2 AC m of t plus k. So you can write cot inverse of 1 by 2 AC m of t plus k whole divided by 1 by 2 AC m of t. Okay, we are now looking at the envelope of the signal. So this is one we want now, envelope. Because we are going to give the signal to the envelope detector. Why are we finding out the envelope? If you look at the diagram, we are going to use the envelope detector. Therefore, we need to find out the envelope of the signal. That envelope of the signal is denoted by R of t. Okay, the envelope detector will be the same that we used in the DSB signal with the carrier. Okay, the envelope detector or the diode detector will remain the same for here also. We are trying to understand the nature of E of t, that is our concern here. In any case, theta of t is not relevant here. Okay, we don't want theta of t. Okay, we are only looking at the envelope. So let us not worry about theta of t. We will consider only R of t. Now you can ask, are we avoiding totally the phase coherence? Because as I said, we are not worrying about theta of t. But the answer is no. Okay, we are not totally avoiding the phase coherence. Okay, we are adding a local carrier. What is a local carrier? If you look at the figure, the local carrier is A times cos omega ct. Okay, to the incoming signal, which essentially means that you recover a phase coherence here. Okay, here we assume the phase difference is 0. Okay, therefore the coherence issue remains to be discussed. Okay, we will certainly discuss that. Now let us look at the expression for the envelope. What is your R of t? Your R of t is square root of 1 by 2 AC m of t the whole squared plus 1 by 2 AC m cap of t the whole squared. Now I would like the envelope to follow the message signal m of t. M of t. Okay, so the envelope should follow the m of t. Now you can ask a question at what condition your R of t follows m of t from this given expression. I mean, under what condition will R of t approximately follow m of t? Under what condition R of t m of t? That is a question in front of us. If we answer that question, then almost our job will be over. Okay, you make it k a little larger. Where is the k? Oh my god, I did not write the k properly. I am sorry. Yeah, this k I missed out. So this is going to be AC by 2 m of t plus k whole squared. I am sorry. Okay, you make k as big as possible so that this will be significantly small. Okay, so that is what precisely we will do. We will choose our local carrier to be added in sufficiently large quantity, that is sufficiently large amplitude. So you make this k as large as possible. This k make as large as possible at the demodulator. If you do that, we can approximately write the envelope as follows. So this whole thing will be bigger than this second term. Okay, so the first term dominates over the second term. In that case, 1/2 AC by 2 m of t plus k will be much larger than AC by 2 m cap of t. The moment you receive the signal, no, that time this m of t will be very low and AC also very low at the receiving end. So you put some large number, probably this might be in terms of, let's say, millivolts, and you give some tens of volts, like some, let's say, 10 volt like that. Therefore this quantity will be much lesser, AC by 2 m cap of t. So the whole thing will be 10.10 millivolts like this, and this will be around 10 millivolts like that. Okay, much larger. So if you make this kind of assumption, that is 1 by 2 AC m of t plus k is much greater than AC by 2 m cap of t for all time, which can be easily done by choosing k to be sufficiently a large constant with respect to other signal, then we can approximate R of t as follows. R of t is equal to square root of AC by 2 m of t plus k the whole square, and plus you can make it this 0, very less. So this will be equal to okay, this is not equal, actually it is approximately equal. Therefore R of t approximately equal to AC by 2 m of t plus k. Okay, now if you pass it through the low pass filter, you can ignore the k. Okay, we get an envelope which is proportional to the message itself. Therefore your R of t is proportional to your message signal m of t itself. Okay, so if envelope follows the message, then the envelope detector obviously would produce the output which is proportional to the envelope. See, my envelope is following the input signal. Okay, so my envelope is following the message. If you get this kind of conditions, then you can use the envelope detector. So whenever your envelope follows the message signal, then you can go for envelope detector. You can use simple diode, resistor and capacitor. Okay, so that's it. So this method gives you an alternative method for demodulating the single sideband signal. So even in this situation, we would require the local carrier. If you look at the figure, we require the local carrier to be in phase and frequency synchronization. See, the incoming signal frequency and this frequency are synchronized. Okay, even in this method also, we need a phase coherence and frequency synchronization. These two are needed. In the previous method also we need phase coherence and frequency synchronization, and here also we need a phase coherence and frequency synchronization. Then you can ask a question, why are we using this than the first method? In the first method, if you recall, what you do, your local carrier is multiplied, right? Your cos omega c t is multiplied by the incoming single sideband modulated signal. This is your synchronous demodulator. But if you look at the carrier reinsertion demodulator, you are not multiplying, you are simply adding. Okay, so we would recover this addition is much more easier, and it is easier to manage than the multiplication operation. Okay, this is a little complicated. Multiplication. Okay, but if you give it an adder, then it is easier compared to this guy. So the carrier reinsertion method is easier to manage, okay, at least for applications like speech signals. For example, if there is any phase mismatch in the synchronous demodulator, if there is any phase mismatch, then there will be some error, because your output is m of t times cos of theta of t. But one can adjust the phase by continuously changing the frequency. Okay, so one can adjust the phase and the frequency of the local oscillator manually tuning. Okay, so therefore till you get a distortionless output. Suppose let's say you give this guy to a demodulator, okay, demodulator, and in case if you get some distorted output, then what you do, you keep on tune this guy till you get a distortionless output. So this is possible, at least for the speech signal. Okay, it is not as sensitive as the coherent detector. Coherent detector is very sensitive to phase distortion, but this is not that much sensitive. So just like tuning the receiver, you can tune till you get a phase and frequency synchronism, or till you get your speech quality back. So it is easy to do in this case than in the other cases, and therefore this is preferred over that system. So carrier reinsertion method is preferred over the synchronous demodulator. The local carrier frequency and phase can be manually tuned. That's what I said. This is your local carrier and it can be manually tuned. Manually tuned till you get a distortionless output. Of course, one doesn't use SSB music ever, okay, we will not use for music signal. So just for an example I am telling you. So typically for speech, till you get your quality back and the intelligibility is good, we can keep on tune it. So theoretically it can be done. Okay, theoretically the synchronous demodulation can be done and the carrier reinsertion can be done, but if you come to the practical, then this carrier reinsertion will be very easy. Okay, so in other words, if you do some analysis, you will find that carrier reinsertion method is less sensitive to the phase and frequency errors than the synchronous demodulation. Synchronous demodulation is more sensitive to the phase and the frequency errors than the carrier reinsertion method. So that is why we always prefer the carrier reinsertion method than the synchronous demodulator, at least for SSB modulation. So the final point I would like to write down is frequency and phase can be manually tuned. Right quality of M of T. Okay, so that's about single sideband modulation. So single sideband modulation is good if you want to save the bandwidth. It is a little more tricky to demodulate like we have just seen. But these complexities one ignores if bandwidth is of very major concern to us. If you want to save bandwidth, we will live with the complexities. We will try to do whatever is required to make a carrier working very well. But if the receiver happens to become very complex in the process, we don't mind, because bandwidth is important. It is an important resource for us. As I said, bandwidth is very important resource, and power also very important resource. So whenever you want to save the bandwidth, we will live with the complexities. If you want to save the bandwidth, then live with the complexities. No other way. Okay, so if the receiver happens to become very complex in the process, we don't mind, no problem. At the end we are saving the bandwidth, right? So in such a case, we are ready to spend the money, and we are ready to accept the complexity of the receiver, because the bandwidth is important for us. Okay, like as I said, there are no two different ways of saving the bandwidth. They are equivalent ways depending on the application. You can choose one over the other. Like if you recall from the previous lecture, we said quadrature amplitude modulation, QAM COM, or quadrature multiplexing. Okay, so if you have the application where you would like to actually transmit two messages on the same carrier, then quadrature multiplexing is a good alternative. If on the other hand you are transmitting a large number of messages, then in the same overall frequency band, it is much more convenient to use single sideband modulation and put them in a large number in the adjacent bands. Suppose you have a large bandwidth like this, then you want to send many signals. So like this, you give for user 1, and then this bandwidth for user 2, and this one for user 3, user 4, like that you can keep on send data. Okay, so you have a large number of messages, U1, U2, U3, U4, U5, like that. You want to send it through some overall frequency band. My overall frequency band is this one. So you are dividing the frequency band in terms of subbands like this. So in fact, this is called something frequency division multiplexing. Sometimes you have the bandwidth, same available bandwidth like this, and in this you want to send two messages in the same available bandwidth. Okay, if you recall from your DSBSC, this is FC. Okay, this is B and minus B. Now what you do in this case, you transmit in this bandwidth of 2B, again send two signals, let us say M1 and M2. This we have already seen, something called a quadrature multiplexing. That means what? M1 of t is multiplied by cos omega ct plus the second message signal is multiplied by the same carrier, but that carrier is quadrature with the first one, that is sin omega ct. This is your quadrature carrier multiplexing. Okay, so you can do quadrature multiplexing in each band, which is twice the SSB. Here also again the bandwidth is twice. Bandwidth is 2B and two message signals you are transmitting. So there are various alternatives, okay, which are possible. Just we have a number of techniques which are available, and which technique you actually adopt will depend on the applications. Okay, so as we go along, we will consider some applications where frequency division multiplexing will enable us to put a large number of messages in adjacent sidebands, and we use in that situation we use single sideband modulation. So single sideband modulation is especially used whenever we want to do something called frequency division multiplexing. Okay, you have a large chunk of spectrum and you split the spectrum into small chunk. So in that what you do, allocate a number of messages for each chunk. Each small chunk you allocate one message. Okay, so this is something called frequency division multiplexing. So that's it about SSB demodulation. In the next lecture, we will discuss on vestigial sideband modulation. Okay, that also comes under the category of suppressed sideband modulation. So SSB and VSB both are falling under suppressed sideband modulation. So one more technique, VSB, that we will discuss in the next lecture. Thank you very much.